The Elotri was about to go back on the water with a new engine system in late 2025, and as a designer, I'd always wanted to make my own propeller. On my 10-metre sailing catamaran Pulse, I have designed and built most components, including the mast and sails. I've really enjoyed the sail-making part of this project. What's interesting about wings and foils is there is still no scientific agreement about how a wing works. So I figured, what's the worst that can happen about designing my own propeller? With 3D printing available, to get the design shape would be so much easier than handcrafting one and getting it balanced and consistent between blades. Now the Elotri is an 800 kilogram solar electric boat. As noted in other videos here on this channel, it is defined by towing weight and so relatively light battery pack and motor. The engine is 3 kilowatts or 4 horsepower with an 11 kilowatt hour battery pack. So there's very limited power and energy efficiency is everything. Back in 2008, I was involved with one of my designs in the Friesland Solar Electric Boat Race. One of the takeaways from this was that many propeller designs were tried, but at the time, a very high aspect two-bladed prop going slowly always came out the best. A model aircraft propeller was the go-to at the end. My thinking was that conventional propellers that are available are low aspect, high area and very heavy, completely inappropriate for the Elotri, so I needed to make my own. I purchased a large 3D printer, discovered that PLA with carbon fiber was available, and by only the third thing I printed, it was a full-size propeller, despite a vertical learning curve. It's fascinating watching a propeller being printed for the first time. Not trusting the 3D print material though, I added carbon fiber to the blades in 3 stages, plus carbon discs on the hub ends. Then I somewhat ambitiously clear finished it, which looked great, but a slow process of sanding. The first few trips were taken tentatively, but gradually the load was increased on the prop. It felt very efficient at low output and got the boat to its 5-knot hull speed easily, but it did seem to aerate at full revs. At the time I blamed ventilation from air coming in under the shallow rear hull area. It felt like there was more thrust and maybe speed available than I was getting. So it was on to prop 2. From the solar boat race, I thought I needed to at least try a 2-bladed prop. So I designed the same prop with 2 blades, not 4, printed it out and added more carbon fiber. This time I used lots of undercoat and carbog, autofiller, to get it to a fair surface. From my time back in the America's Cup in Bermuda working on foils, I knew there was no need to get a glossy surface. 800 grit would do, so that became my propeller surface standard. Unfortunately, this prop 2, the 2-bladed one, was rubbish. Useless in reverse and struggled to get past 3.5 knots going forward. Eventually, during testing, it suddenly started to vibrate. Back at the ramp, it was obvious why. A blade had broken off. As it was the same construction as the 4-bladed one, I assumed it was simply too much individual blade loading. So that was the end of that direction. 3 was the conservative 4-bladed version with much less pitch than the first 2, in case I simply was demanding too much from the engine and the boat got to 5 knots and struggled to go faster. It felt like an effective prop on the water without setting records. By now on prop 1 I've also sharpened up the leading edges from a radiused aerofoil section to more of a knife. I was convinced the blades were aerating from the tips and so limiting their performance. Or cavitating, but I didn't want to even admit that at this speed. So prop 4 was a heavily raked version of prop 1 to make sure any aeration would flow to the tips and go on downstream. It featured sharp leading edges and ogival sections as opposed to aerofoil ones. This seemed to perform well with good efficiency but no change to top speed. The aeration on the wake felt reduced. By now my imagineering was going really well. It was costing perhaps $50 in materials and a day's work for each one, and it felt like worthwhile research. At these displacement speeds, maybe I should be looking at quart nozzle type setups, which have a fixed aerofoil around the prop fan blades. Now that seemed a big change, but why not attach the foil to the blades? I found someone who had done it years ago once. Rather than just a ring, the outer area could be an airfoil section to provide some lift, not just drag. The idea was to get area to the tips without worrying about tip loss. Then why not have smaller inward fins so that all of the outer ring had positive forward lift going on? And let's go for 5 blades for extra area and balance. So I came up with this design. It was so complex, but it also felt stiff and strong. So I chose not to glass it. Well, the first test of prop 5 lasted about 10 seconds and it failed at the hub. Obviously more resistance to turning than the others, so I was hoping that meant more thrust. The problem was the 3D printer wasn't printing solid at the hub, so I filled this area with glue powder filled epoxy. Later testing had the prop feeling very effective forward and exceptional in reverse. Still the same top speed. Next, it was a further couple of 5-bladed propellers with lots of area, rake and curve on the blades. By this stage my 3D printer was fighting back, not giving good prints. Prop 6 was smaller diameter than prop 7 and they were both effective but inconclusive. Now during this testing I was trying to get speed per watt information. The problem is there is always a variety of wind and tide conditions that throw up unknown variables between test days. Here's some data between some props, but I didn't trust it. So it was time to get better data. I purchased a digital scale and over a few weeks launched the boat, tied it loosely to the dock and had scales on a bridle to the marina. With Bluetooth to the output figures and allowing for different solar conditions, I set the engine at 500, 1000 and 1500 watts and took the thrust readings in kilograms. This seemed the best way of comparing real life thrust, even if it was at rest, of the different propellers. By now, I'd convinced myself that prop 5, the ring prop, was the best, so it was up first. Thrust figures of 13, 24 and 36 kilograms seemed impressive, so I continued with props 4, 6 and 7. Props 1 and 3 I considered part of the process, but unlikely to feature. That assumption proved to be wrong. So what is the conclusion? Well, I was right at the start with the propeller 1. If I have lots of people aboard and a big load, then the lower pitch prop 3 is probably better, but there seems little promise with the others when the numbers are so different and low. Yes, they could be better at speeds than these static tests show. The pleasant river trips we've done on the Elotri typically are between 3.5 and 4 knots of speed, so between 500 to 1500 watts of output power. The high aspect 4-bladed props seem the most efficient at that. Yes, I would like to get the Elotri going faster than 5 knots of course, but at such low horsepower the speeds we are going is still an accomplishment. Of course there's plans for more development, so hit subscribe and the bell to see the next installment of the development of the Elotri. Thanks for watching.